Welcome to the IPv6 Fundamentals video course. The most important goal of this course is to provide a thorough yet easy to understand introduction to IPv6. This course is also intended to provide a foundation in IPv6 that will allow you to build on it. This includes explaining topics that might be a little more challenging to grasp. There is a great deal to learn about IPv6. It's not difficult to learn, but involves multiple protocols and processes that might be new to you. And it is definitely much more than just becoming familiar with a larger address. The following few slides provide an overview of all the lessons we will cover. Our course is divided into 6 modules, plus the Super Lab as an additional module, making it a total of 7 modules. Introduction to IPv6. IPv6 operations. Routing IPv6. IPv6 services. IPv6 and IPv4 transition techniques. IPv6 security. Super Lab. Each module is divided into lessons, totaling 26 lessons. Don't be overwhelmed by all the details. It isn't necessarily important that you understand it all, but I did feel it necessary not to leave out or hide these details from you. The objective of this course is to explain IPv6 as clearly as possible. I feel it's better to revisit some of the more advanced topics after you have a more complete understanding of the entire IPv6 topic. Welcome to Module 1, Introduction to IPv6. In the first lesson of this module, you will learn about the need for a new network layer protocol, which is IPv6. We will see that the constantly growing Internet requires a new network layer protocol to meet the demands of its users. We will talk about the concerns and limitations of IPv4, how IPv6 was developed, and how it resolves the limitations of IPv4 while offering other advantages as well. A review of the Internet protocol history will also be briefly discussed. Internet Protocol version 4, IPv4, is the current Layer 3 protocol used on the Internet. IPv4 was designed for a few hundred computers, but has still survived over 30 years. However, due to its rapid growth in the last decade, IPv4 address space is almost depleted. From its early years until 1995, there were only 16 million Internet users worldwide, even with the advent of the World Wide Web. In 2001, the number of Internet users reached 500 million. In 2005, the number of Internet users reached 1 billion. And finally, in 2014, the number of Internet users reached 3 billion. This diagram shows the number of networks in the Internet routing table from 1996 to 2014. We can see that the size of the Internet routing table increased rapidly. After initial explosive growth, there was another one back in 2007. In 1996, the number of routes in the Internet routing table was around 25,000. In 1998, the number of routes in the Internet routing table was around 50,000. In 2001, the number of routes in the Internet routing table was around 100,000. In 2005, the number of routes in the Internet routing table was around 150,000. In 2007, the number of routes in the Internet routing table was around 200,000. In 2010, the number of routes in the Internet routing table was around 300,000. And finally, in 2014, the number of routes in the Internet routing table reached 500,000. The actual number of devices increases dramatically when taking into account that today's users usually have multiple Internet-enabled devices, such as smartphones, tablets, and laptops. Today's Internet is much more than just web pages, email, and file transfers. With the explosive growth of mobile devices and peer-to-peer networking, along with the potential impact of Internet-ready consumer goods, we have gone from just an Internet of computers to an Internet of Things. Cisco predicts that 37 billion new things will be connected by 2020, and the Internet of Things will quickly evolve into the Internet of Everything. Through the connections in the Internet of Everything, even the smallest things, thermostats, cars, lights, or alarms, will have the ability to communicate with each other and shape our planet. Think of all the possibilities when Internet-ready devices begin to communicate with each other. Initial design of IPv4 did not anticipate such a growth of the Internet, and this created many issues. The IPv4 addressing system uses 32-bit address space, which allows for a theoretical maximum of 4.3 billion addresses. This 32-bit address space is further classified to usable A, B, and C classes, and there was some inefficiency in the allocation of these addresses over the years, which limits the number of available public IPv4 addresses. Many addresses that were allocated to many companies were not used, and this created scarcity of IPv4 addresses. Even if it were possible to reassign the entire IPv4 address space more efficiently, it would not only be impractical, but would also only act as a very short-term solution. Due to the scarcity of IPv4 addresses, many organizations implemented Network Address Translation (NAT) to map multiple private IPv4 addresses to a single public IPv4 address. By using NAT, we can map many internal private IPv4 addresses to a single public IPv4 address, which helps in conserving IPv4 addresses. But there are some security limitations when using NAT. It can't be used with IPsec in transport mode, because the NAT translation breaks the integrity check. Network security threats were not anticipated at the time IPv4 was developed. Internet Protocol Security, IPsec, is a protocol suite which enables network security by protecting the data being sent from being viewed or modified. IPsec provides security for IPv4 packets, but it is not built into IPv4, it is optional. Networks are expanding, and many new computers and devices are using IP. The configuration of IP addresses, static or dynamic, should be simple. The eventual exhaustion of IPv4 address space was recognized in the early 1990s. With the advent of the World Wide Web, there was an explosion in the size and diversity of the Internet population. With the development of the Hypertext Transfer Protocol, HTTP, followed by the first web browser, all of a sudden, people who never owned a personal computer were accessing the Internet. It was becoming clear that 4.3 billion addresses were not going to last for long. The size of the Internet routing table was increasing rapidly, and the explosion of the number of Internet users generated a consensus that it was time to begin designing and testing a new network layer protocol as the successor to IPv4. Various projections, including a study done by the IETF in the early 1990s, predicted that the Internet would run out of IPv4 address space. So, in the early 1990s, IETF began development of a new version of IP, known as IP Next Generation, or IPNG, which later became IPv6. This, however, was a long-term solution, and a short-term solution was needed immediately. Several steps were taken, including NAT, Private IP Address Space, and Classless Interdomain Routing, CIDR. In addition to increasing the size of the address space, this was also a unique opportunity to fix the limitations of IPv4 and develop a protocol to ensure reliable growth and enhanced performance for the future. In 1995, IETF published RFC 1883, Internet Protocol version 6, IPv6 specification, which later became obsolete and was replaced by RFC 2460 in 1998. Regional Internet Registries, RIRs, began allocating IPv6 addresses to their customers in 1999. Adoption was slow at first, but in 2007, RIRs began receiving significantly more requests for IPv6 address space. In 2000, many vendors began addressing IPv6 support to their mainstream products. Cisco systems added IPv6 support with Cisco iOS software release 12.2.2t. Linux vendors started supporting IPv6 in 2000, and Microsoft announced IPv6 support with Windows XP in 2001. Why do you need to start thinking about migrating to IPv6 now if your network runs just fine with IPv4? Although there isn't a single reason that forces everyone to immediately move to IPv6, there are several reasons for network administrators to at least begin preparing for the migration. The most notable of these reasons is that we are simply running out of IPv4 address space. It is said that the main reason for IPv6 is preserving the Internet and allowing it to move forward. Several of the main benefits and features of IPv6 are: extended address space. IPv6 provides 128-bit addresses compared to 32-bit addresses with IPv4. This represents an enormous number of addresses, 2 to the 128th power, enough for every grain of sand on Earth. When you ask most people what they know about IPv6, they will probably refer to the larger address space, but IPv6 is much more than just that. It is a more efficient and elegant protocol with auto-configuration and neighbor discovery. Stateless auto-configuration. IPv6 provides a configuration mechanism where hosts can self-generate a routable address. IPv4 auto-configured addresses are usable only on the local subnet, link local, and are never forwarded by a router. Eliminates the need for NAT or PAT. Because of the large number of public IPv6 addresses, there is no longer a need for NAT or PAT, port address translation. Customer sites from the largest enterprises to single households can get a public IPv6 network address. This avoids some of the NAT-induced application problems experienced by applications such as voice over IP, video conferencing, and other peer-to-peer applications. eliminates broadcasts. IPv6 does not use Layer 3 broadcast addresses. Whereas in IPv4, Address Resolution Protocol (ARP) uses broadcasts, IPv6 employs solicited node multicasts, a more efficient and selective technique to accomplish the same purpose. There is also an all-node multicast address that essentially has the same effect as an IPv4 broadcast. Transition tools. IPv6 has a variety of tools to help with the transition from IPv4 to IPv6, including tunneling and NAT. Tunneling encapsulates the IPv6 packet into an IPv4 packet so that it can be delivered over IPv4-only networks. NAT provides a mechanism to translate an IPv4 address to an IPv6 address, or an IPv6 address to an IPv4 address. IPv4 can also be tunneled over IPv6. When we are talking about IPv4 and IPv6, you might ask yourself, where are IPv1, v2, and v3? IP was created when its functions were split from an early version of TCP that combined both TCP and IP functions. TCP evolved through 3 earlier versions and was split into TCP and IP for version 4. That version number was applied to both TCP and IP for consistency. Even though the name seems to imply that it's the 4th iteration of the key Internet Protocol, version 4 of IP was the first that was widely used in modern TCP/IP. Now you might ask yourself, okay, that explains versions 1 to 3, but what about IPv5? IPv5 was once, in the late 1970s, an experimental draft proposal in the IETF defining a real-time streaming protocol. It did not result in a standard deployed on production networks. It is actually called the Internet Streaming Protocol, ST, and later ST2. Internet Streaming Protocol version 2 was not designed as a replacement for IPv4. The idea was that a multimedia application would use both protocols, IPv4 for the transfer of traditional packets, and ST2 for packets carrying real-time data. Although it was never recognized as IPv5, when encapsulated in IP, ST uses IP protocol number 5. In other words, although it was never implemented, the designation IP version 5 was already taken. By the way, IPv4 uses IP protocol number 4, and IPv6 uses 41. After watching this lesson, you should have a better understanding of the limitations of IPv4 and know why it is necessary to begin migrating to IPv6. How we use the Internet today is much different than it was when IPv4 was developed, and although the combination of classless interdomain routing, NAT, and private addressing has helped slow the depletion of IPv4 address space, we will eventually run out of IPv4's 4.3 billion addresses. IPv4 and IPv6 can and will coexist for the foreseeable future. IPv6 includes tools and migration strategies that allow both protocols to coexist. IPv6 provides more than enough globally unique addresses to support the growth of the Internet. But in addition to a larger address space, IPv6 offers additional enhancements, such as stateless auto-configuration and expanded address space without NAT. Welcome to Module 1, Introduction to IPv6. In the second lesson of this module, you will learn about the features of IPv6. This lesson examines the IPv4 and IPv6 fields and headers, and explores both the similarities and the differences in those two protocol versions. In addition to the main IPv6 header, extension headers are also examined. At the end of this lesson, we will have a lab exercise in which we will complete a packet analysis of both IPv4 and IPv6 using Wireshark. You may be familiar with the structure of the IPv4 header, or at least with some fields in it, but to help you better understand the IPv6 header, we will first review the fields in the IPv4 header. The first header field is the 4-bit version field. For IPv4, this has a value of 4, hence the name IPv4. Internet header length, 4 bits. This is the length of the IP header in 32-bit words, including any optional fields. Since an IPv4 header may contain a variable number of options, this field specifies the size of the header and, in effect, points to where the IP header ends and the data or payload begins. Differentiated Service Code Point, DSCP, 6 bits, and Explicit Congestion Notification, ECN, 2 bits, were originally defined as the 8-bit type of service field. DSCP helps provide quality of service (QoS) features by offering different degrees of services. When multiple packets are queued to be transmitted from the same interface, the DSCP value can be used to decide which packet is sent when. ECN allows end-to-end notification of network congestion without dropping packets. ECN is an optional feature that is only used when both endpoints support it and are willing to use it. It is only effective when supported by the underlying network. Total length, 16 bits. Defines the entire packet, fragment, size in bytes, including header and data. This is a 16-bit field, so the maximum size of an IPv4 packet is 65,535 bytes, while the minimum length packet is 20 bytes, 20-byte header plus 0 bytes data. The next 3 fields, identification, flags, and fragment offset, are used for packet fragmentation and reassembly. The design of IP allows routers to fragment IP packets when an MTU, maximum transmission unit, along the path is smaller than the sender's MTU. If a router receives an IPv4 packet that is larger than the MTU of the outgoing interface, this packet can be fragmented depending upon the options in the IPv4 header. Sometimes packets are fragmented into multiple packets at the source. The final destination of the IP packet is responsible for reassembling the fragments into the original full-size IP packet. Identification, 16 bits. Most messages sent over the network consist of many packets. Each packet within the message has a unique value using the identification field. When a packet needs to be fragmented into two or more packets, this identification field is common in all the fragmented packets to help the receiver to reassemble these fragments. Flags, 3 bits. This 3-bit field is used to control or identify fragments. These bits are, from high order to low order, bit 0, reserved, must be 0. Bit 1, don't fragment, DF. Setting to 1 means that this packet should not be fragmented. Setting to 0 means that this packet can be fragmented if needed. Bit 2, more fragments, MF, is used to indicate whether this is the last fragment, 0 bit, or whether there are more fragments to follow, 1 bit. Fragment offset, 13 bits. Measured in units of 8-byte blocks, 64 bits, it specifies the offset of a particular fragment relative to the beginning of the original unfragmented IP packet. Basically, it notifies the receiver where to align this fragmented packet in relation to the other fragmented packets. The first fragment has an offset of 0. If the packet is not fragmented, this value is also 0. Time to live, TTL, 8 bits. Ensures that packets do not live in the network for an indefinite period of time, as in the case of a routing loop. The TTL is decremented by 1 each time a router receives the packet. When the field reaches a value of 0, the packet is discarded, and an ICMPv4 time exceeded message is sent to the source of the packet. Protocol, 8 bits. Defines the protocol used in the data portion of the IP datagram. Header checksum, 16 bits. Is used for error checking of the header for protection against any corruption in transit. When a packet arrives at a router, the router calculates the header's checksum and compares it to the checksum field. If the values do not match, the router discards the packet. Errors in the data field must be handled by the encapsulated protocol. Both UDP and TCP have checksum fields. Source address and destination address, both 32 bits. The source address is the packet sender's IPv4 address. Note that this address may be changed in transit by a network address translation device. The destination address is the packet receiver's IPv4 address. As with the source address, this may be changed in transit by a network address translation device. Options: variable length. This field is optional, so it might or might not appear in the IP packet. It is variable in size and not included in most packets. This is the basic structure of the IPv6 header, or what is sometimes referred to as the main IPv6 header. The main IPv6 header can also include one or more IPv6 extension headers, which are explained later in this lesson. The first header field is the 4-bit version field. For IPv6, this has a value of 6, hence the name IPv6. Traffic class, 8 bits. Like in IPv4, the bits of this field hold 2 values. The 6 most significant bits are used for differentiated services code point, which is used to classify packets. The remaining 2 bits are used for explicit congestion notification, which allows end-to-end notification of network congestion. Flow label, 20 bits. Was originally created for giving real-time applications special service, but, when set to a non-zero value, now serves as a hint to routers with multiple outbound paths that these packets should stay on the same path so that they will not be reordered. Payload length, 16 bits. Is the size in bytes of the payload following the main IP header, or, in other words, the packet's data portion, including any extension headers, which are considered part of the payload. Unlike the total length field in the IPv4 header, which includes both the IPv4 header and the data, the IPv6 payload length field only specifies the number of bytes of data. It does not include the main IPv6 header. Next header, 8 bits. Specifies the type of the next header. When extension headers are present in the packet, this field indicates which extension header follows. When there is only the main IPv6 header and no extension headers, the next header field specifies the protocol carried in the data portion of the IPv6 packet, similar to the protocol field in the IPv4 header. Hop limit, 8 bits. Is equivalent to the time to live field in IPv4. This value is decremented by 1 at each intermediate node. When the field reaches the value of 0, the packet is discarded, and an ICMPv6 time exceeded message is sent to the source of the packet. Source address and destination address, both 128 bits. Source address is the packet sender's IPv6 address. Destination address is the packet receiver's IPv6 address. Let's summarize some of the important differences between the two protocols. First, we will start with header comparisons of the IPv4 fields that have the same names as those in IPv6. Version. The value is 4 in IPv4 and 6 in IPv6. Source address and destination address. The biggest differences are the 32-bit addresses in IPv4, which have been increased to 128 bits in IPv6. We will continue with IPv4 fields which names changed in IPv6 with functional differences in some cases. DSCP and ECN changed to traffic class. Both use 6-bit DSCP for packet classification and 3-bit ECN for congestion control. Total length changed to payload length. IPv4's total length field includes both the IPv4 header and the data, whereas the IPv6 payload length field only specifies the number of bytes of data or payload, including any extension headers, and does not include the main IPv6 header. Time to live changed to hop limit. This has the same function in both IPv4 and IPv6, with the name being more reflective of its actual use in IPv6. Protocol change to next header. In IPv4, this indicates the protocol being carried in the IPv4 data or payload. This same function exists in the next header field in IPv6, but can also indicate the existence of an extension header following the main IPv6 header. Now we will examine IPv4 fields that are removed from IPv6. Internet header length. This field is not needed in IPv6 because the main IPv6 header has a fixed length of 40 bytes. Any additional headers are linked as indicated in the next header field. Identification, flags, and fragment offset. These fields are used for fragmentation in IPv4. Fragmentation is handled differently in IPv6, using the fragment extension header. Header checksum. Layer 2 data link layer technologies, such as Ethernet, perform their own checksum and error control. Upper layer protocols, such as TCP and UDP, also have their own checksums, and therefore a checksum at layer 3 becomes redundant. A UDP checksum, which is optional in IPv4, is mandatory in IPv6. Options. Options in IPv4 are now handled using extension headers in IPv6. The last difference in header comparison is a new field in IPv6. Flow label. This is used to tag a flow of IPv6 packets as a hint that these packets should stay on the same path. There are several other important differences in the two protocols. MTU. IPv4 requires that every node must be able to forward an IP packet of 68 bytes without any further fragmentation. Every IPv4 node that is the final destination of the IPv4 packet must be able to receive an IPv4 packet of a minimum size of 576 bytes. IPv6 requires that every link have a minimum MTU of 1280 bytes, with a recommended MTU of 1500 bytes. UDP. UDP checksum field in IPv4 is optional. Although the protocol remains the same in IPv6, the checksum field is mandatory. This is because the IPv4 header has its own checksum field, but this field has been removed in the IPv6 header. Fragmentation. Only the IPv6 packet's source node can perform fragmentation. If an intermediate node, such as a router, receives an IPv6 packet that needs to be fragmented, it will discard the packet and send an ICMPv6 packet too big error message back to the source. Extension headers are optional and follow the main IPv6 header. The intention of extension headers is to provide flexibility to the main IPv6 header for future enhancements without having to redesign the entire protocol. This also allows the main IPv6 header to have a fixed size for more efficient processing. Immediately following the mandatory main IPv6 header, there can be 0, 1, or several extension headers. A field common in all extension headers is another next hop field, which indicates whether another extension header or the protocol payload is to follow. Therefore, the last extension header will always specify which protocol is encapsulated as the payload. There are currently 6 extension headers. Hop-by-hop options. With a decimal value of 0, this is used to carry optional information which must be examined by every router along the path of the packet. Routing. With a decimal value of 43, this allows the source of the packet to specify the path to the destination. Fragment. With a decimal value of 44, this is used to fragment IPv6 packets. Encapsulating Security Payload, ESP. With a decimal value of 50, this is used to provide authentication, integrity, and encryption. Authentication Header, AH. With a decimal value of 51, this is used to provide authentication and integrity. Destination options. With a decimal value of 60, this is used to carry optional information that only needs to be examined by a packet's destination node. No next header. The next header value of 59 indicates that there is no data following this header. This is just a placeholder, indicating that there is nothing after this header. If the payload length indicates that there are additional bytes beyond the header, those bytes will be ignored. When multiple extension headers are used in the same packet, those headers appear in the following order. Main IPv6 header. Hop-by-hop options. Destination options, before routing header. Routing. Fragment. Authentication. Encapsulating security payload. Destination options, before upper layer header. Upper layer protocol. Now we will jump to the lab exercise, in which we will complete a packet analysis of both IPv4 and IPv6 traffic using Wireshark. We will use this simple topology where we have two routers, R1 and R2, connected back-to-back using serial 1/0 interfaces on which they run both IPv4 and IPv6. IPv6 addressing and enabling IPv6 will be covered in detail in the following lessons. So for now, let's just configure per diagram what needs to be configured without going into too much detail. First, we are going to configure R2. We need to enable IPv6 unicast routing because it is disabled by default. We also need to enable IPv6 Ceph processing, or Cisco Express Forwarding, because it is also disabled by default, and we are going to need it for capturing IPv6 traffic. Now we need to configure IPv4 and IPv6 addresses. We will use a simple 10.0.12.0/24 network between the routers for IPv4 and a bit more complicated network 2001:7052:E1cc A012 /64 for IPv6. Router R1 will use the first possible address from those networks, 1, and router 2 will use 2. We need to enable the interface because by default it is shut down, and that is all that we need on router R2. We will repeat the same procedure on R1. Enable IPv6 unicast routing and IPv6 Ceph. Configure IPv4. And IPv6 addressing. And before enabling the interface, we need to configure clocking, because this side is DCE. Embedded packet capture configuration is beyond the scope of this course. These features require Cisco iOS release 12.4.20T or later. So for a detailed explanation of the commands, you can use search for the configuration guide on cisco.com. First, we need to define the capture buffer, which we are simply going to name buffer. Then, we need to define the capture point for IPv4 using Ceph. We are going to name it capture underscore point v4. And it will monitor the traffic on serial 1/0 interface in both directions. We will do the same for IPv6 traffic. Using capture point, capture underscore point v6. Now, we need to associate capture points that we have created with the buffer that we configured in the first step. Last, we need to start the capture points that we have configured. For testing purposes, we are going to ping R2, both IPv4 and IPv6 addresses. And now we need to stop the capture point so that we can export it to the TFTP server, which needs to be reachable. We will name this capture r1.pcap. It looks like my TFTP server is having connectivity problems, and it will probably time out. Okay, the TFTP server is now reachable, so we can export the pcap file to it. And now we can analyze this pcap file using Wireshark, which is a free network protocol analyzer for both IPv4 and IPv6. First, we are going to have a look at IPv4 traffic. Now, you should be familiar with various IPv4 headers. Version. This is version 4. Header length is 20 bytes. DSCP is not set. ECN is also not set. The total length is 100 bytes. Identification is 25. Flags are not set. Fragment offset is 0 because this packet is not fragmented. Time to live is 254. Protocol in payload is 1, which is ICMP. Header checksum is correct. Source address is 10.0.12.2, which is R2. And destination address is 10.0.12.1, which is R1. This IPv4 packet is carrying ICMP traffic, specifically an echo reply from router R2 to R1. Now, we are going to analyze the IPv6 traffic, and you should be familiar with various IPv6 headers as well. Version. This is version 6. Traffic class, which stores values for DSCP and ECN, are both not set. Flow label is also not set. Payload length is 60 bytes. Next header is 58, which is a value for ICMPv6 messages. The hop limit is 63. Source address is R2's address. And destination address is R1. This IPv6 packet is carrying ICMPv6 traffic, specifically an echo reply from router R2 to R1. This lesson examined both the IPv4 header and the IPv6 header. It compared the similarities and differences between the two protocols. The IPv6 header has fewer fields, and in many respects, it is a simpler protocol. Some of the fields moving from IPv4 to IPv6 remained the same. Some had name changes with functional differences. Others were removed completely, and there was a new flow label field added. Extension headers were introduced. They provide more flexibility and better efficiency for IPv6. and Wireshark packet analysis has been done for both IPv4 and IPv6. Welcome to Module 2, IPv6 Operations. In the first lesson of this module, you're going to learn about IPv6 addressing. This lesson examines IPv6 addressing and gives a brief introduction to different types of IPv6 addresses. The hexadecimal number system is first reviewed to provide a basis for representation of IPv6 addresses, which is discussed later in this lesson. Different formats of representing IPv6 addresses and the rules for compressing the IPv6 notation are also examined. Subnetting IPv6 addresses is discussed as well, and at the end of this lesson, we will have a short lab exercise, IPv6 addressing. The hexadecimal number system has 16 digits, 0 through 9 and A through F. There are 16 unique combinations of 4 bits, which is half of a byte and is also known as a nibble. So, any 4 bits can be represented as a single hexadecimal digit. Because one hexadecimal digit can represent 4 bits, this means that 2 hexadecimal digits can represent a single byte. IPv6 addresses are 128 bits in length and written as a string of hexadecimal digits. Every 4 bits are represented by a single hexadecimal digit, for a total of 32 hexadecimal values. 4 times 32 equals 128. This is the preferred format. Each X is a 16-bit section that can be represented using up to 4 hexadecimal digits, 0000 to FFFF, separated by a colon, which is also known as a hextet. This results in 8 16-bit sections of the address. 8 times 16 equals 128. The preferred format is the longest representation of an IPv6 address. A total of 32 hexadecimal values are used. Here are the examples of IPv6 addresses using the preferred format. Note that it is not easy to either read or write IPv6 addresses using the preferred format. Besides the preferred format, there are 2 helpful rules in reducing the notation of IPv6 addresses. The first, that is, leading zeros in any hextet can be omitted. This applies only to leading zeros and not to trailing zeros. Otherwise, the address would be ambiguous. Using one IPv6 address from a list of preferred IPv6 addresses, the following example shows how the leading zeros can be omitted. Zeros to be omitted are in bold. Spaces remain to better visualize where the zeros were removed. And this is the final example with omitted zeros. It is important to remember that only leading zeros can be omitted. Otherwise, it would make the address ambiguous. For example, if trailing zeros were also omitted, you wouldn't know what the correct address was. There can only be one correct interpretation. Therefore, only leading zeros can be omitted. The second helpful rule in reducing the notation of IPv6 addresses is the omission of hextets with all zeros, which says that a double colon can represent any single continuous string of one or more hextets consisting of all zeros. This will help further reduce the size of an IPv6 address. The following table illustrates the use of the double colon, showing the preferred address above and the reduced address below. The zeros in bold in the preferred address are replaced by the double colon. Please note that this address can also be written in the following way. But RFC suggests that the double colon should represent the longest string of zeros. As we already mentioned in the previous slide, only a single contiguous string of all zero segments can be represented with the double colon. Otherwise, the address would be ambiguous. Here is an example of an incorrect address using two double colons. There are 4 possible ambiguous choices. As you can see, if 2 double colons are used, there would be multiple possibilities, and you wouldn't know which address is the correct interpretation. Combining both rules can reduce the address even further. The following table illustrates all 3 formats. First, the preferred format. Then, no leading zeros format. Again, spaces were left to better visualize where the zeros were removed. And finally, the compressed format implementing both rules. The following slides review the basic types of IPv6 addresses. They are examined in more detail in the following lesson. In IPv4, there are unicast, multicast, and broadcast addresses. In IPv6, there are no broadcast addresses. The 3 types of addresses in IPv6 are unicast, anycast, and multicast. A unicast address uniquely identifies an interface on an IPv6 device. A packet sent to a unicast address is delivered to the interface identified by that address. An IPv6 address more accurately identifies an interface on a host rather than the host itself. A single interface can have multiple IPv6 addresses, and an IPv4 address as well. There are several types of unicast addresses in IPv6: global, unique local, link local, unspecified, and loopback. An anycast address is a unicast address assigned to several devices. A packet sent to an anycast address is delivered only to one of the devices configured with that address, and it will be routed to the nearest device. There is an anycast address in IPv4, and, like IPv6, it is a common unicast address assigned to multiple devices. But in IPv6, the devices to which the anycast address is assigned are explicitly configured to recognize that it is an anycast address, which is not necessarily the case in IPv4. A multicast address identifies a group of interfaces, typically belonging to different devices. A packet sent to a multicast address is delivered to all the devices identified by that address. All members of the multicast group process the packet. So, the difference between an anycast address and a multicast address is that an anycast packet is only delivered to a single device, whereas multiple devices can receive a multicast packet. There are no broadcast addresses in IPv6. In its place is an all-nodes multicast address. The representation of IPv6 address prefixes is similar to the way that IPv4 address prefixes are written, in classless interdomain routing notation. An IPv6 address prefix, network portion of the address, is represented using the following format: IPv6 address / prefix length. The prefix length is a decimal value indicating the number of leftmost contiguous bits of the address. It identifies the prefix or the network portion of the address. The following slides examine the basic structure of a global unicast address. These are the addresses that are globally routable and reachable on the IPv6 Internet. They are equivalent to public IPv4 addresses. This is the structure of a global unicast address for a typical site. The global routing prefix is the prefix or network portion of the address assigned by the provider, such as an ISP, to a customer or site. It is common for regional Internet registries to have the policy for end sites to use a 48-bit prefix, /48. A big difference between IPv4 and IPv6 addresses is the location of the subnet portion of the address. In IPv4, bits are borrowed from the host portion of the address to create subnets. In IPv6, the subnet ID is a separate field and not part of the host portion of the address, which is known as the interface ID in IPv6. RFC does not specify the size of the subnet ID. The 16-bit subnet ID from the previous slide results from a site receiving a /48 global routing prefix. With a 64-bit interface ID, this leaves 16 bits for the subnet ID, which allows 65,536 individual subnets. The interface ID uniquely identifies the interface on the subnet. The 64-bit interface ID allows 2 to the 64th power addresses for each subnet. The term interface ID is used rather than host ID because a single host can have multiple interfaces, each having one or more IPv6 addresses. Another important difference between the IPv6 and IPv4 addresses is that the all zeros and all ones addresses are legal IPv6 interface addresses. In IPv4, all zeros in the host portion of the address are reserved for the network or subnet address, while all ones indicate a broadcast address. Basic subnetting of an IPv6 address is very straightforward. In many ways, it is much simpler than subnetting an IPv4 address. Unless we are subnetting on a natural octet boundary in IPv4, the specific subnets are not always obvious. It is important to clarify a couple of terms. As illustrated in this figure, there is both a subnet ID and a subnet prefix. The term subnet ID refers to the contents of the 16-bit field used to allocate individual subnets, while subnet prefix refers to the global routing prefix and the subnet ID addressing bits. With a 16-bit subnet ID, the values can range from 0000 to FFFF. Subnetting is painless because we start with 0000 and increment by 1. Remember that this is in hexadecimal, so after 0009, the next subnet ID would be 000A. Subnetting by using the 16-bit subnet ID is easy to perform, as illustrated in this table. The next 16 subnets begin with 0010 and end with 001F. Again, the next 16 subnets begin with 0020 and end with 002F. And so on, until we reach the final 16 subnets, which begin with FFF0 and end with FFFF. Subnetting is not limited to a 16-bit subnet ID. Any number of subnet bits can be chosen for the subnet ID. Just as with IPv4, if you want to extend the number of subnets, or, more likely, reduce the number of hosts per subnet, you must borrow bits from the interface ID. It is important to note that best practice dictates that this should only be done on network infrastructure links. Any segment that includes end systems should stay with a /64 prefix, which is required for supporting stateless address auto-configuration. We will talk about this in the following lessons. As shown here, extending the original /48 prefix by 64 bits, you can use a prefix of /112. By doing so, the first 4 subnets of our extended network would be the following. So, even with extending the subnet ID, subnetting is very straightforward as long as you subnet on a nibble boundary. If we are going to extend the subnet ID, which means using bits from the interface ID, it is best practice to subnet on a nibble boundary. Remember, a nibble is 4 bits, as shown in the following table. In the following figure, we are extending the /64 subnet prefix by 4 bits to a /68. This increases the subnet ID from 16 bits to 20 bits, which allows more subnets but reduces the size of the interface ID. In this case, there isn't any practical reason for doing this except to illustrate the concept. By extending the subnet prefix by 4 bits, or 1 full nibble, we are implementing the best practice of subnetting on a nibble boundary. Using 20 bits, a factor of 4 bits makes it very easy to list the subnets, as illustrated here. For most customer networks, subnetting within a nibble is not recommended. It provides little, if any, benefits, and only makes implementation and troubleshooting more difficult. However, there can be cases when subnetting on a nibble is potentially wasteful, so it is beneficial to subnet within the 4-bit nibble. When you subnet within a nibble, life becomes a little more problematic. In the following figure, we are using a /70 subnet prefix, extending the simple /68 to a more difficult /70. Because it is extended by only 2 bits instead of a nibble 4 bits, it makes the conversion a little more troublesome, although it is perfectly valid. The first subnet is easy enough to figure out. But you can see that the second subnet requires a little more thinking. IPv6 addresses use hexadecimal values to represent each 4 bits. Because a /70 subnet prefix was chosen, the first half, the 2 leftmost bits, of the last hexadecimal digit belongs to the subnet ID, and the other half, the 2 rightmost bits, belongs to the interface ID. So, only the first 2 bits of the last digit of the subnet ID are modified, as illustrated here on the first 4 subnets. Although IPv6 address space is plentiful, there can be reasons for limiting the size of the interface ID within a network infrastructure. RFC recommends employing /127 prefixes on inter-router point-to-point links for what is known as a Neighbor Discovery Protocol exhaustion attack, which is beyond the scope of this course. This figure illustrates our IPv6 network. These first 3 hextets identify the global routing prefix, or IPv6 addresses, that have been received from the provider. The /48 network is divided into 6/64 subnets: 1111, 2222, 3333, A012, A013, and A023. Now we will jump to the lab exercise, in which we will demonstrate basic IP address configuration between 2 routers. You should now have a basic understanding of IPv6 global unicast addresses. Configuring an IPv6 address on a router's interface is very similar to that of IPv4. As shown throughout this course, most of the commands are identical, except the parameter IPv6 is used in place of IP. The command necessary to manually configure an IPv6 address on a router's interface is described in the Cisco iOS IPv6 command reference. This is the home page of the IPv6 command reference. By clicking the links on the left, we are searching for a particular command, which is IPv6 address in this case. Here you can see the complete syntax description for this command. IPv6 address configuration is discussed in Lesson 4. The IPv6 address interface command is only included here to show the similarity between IPv6 and IPv4 commands. The global configuration command IPv6 unicast routing is required to enable a router to route IPv6 packets. This command is also discussed in Lesson 4. Now we will configure the serial 0/0 interface on both R1 and R2 with the appropriate IPv6 address and the prefix length /64. Configure terminal. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001/7052 E1CC A012 2/64. When configuring an IPv6 address in Cisco iOS, there is not a space between the IPv6 address and the prefix length. No shutdown. End. Same procedure on router R1. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001 7052 E1CC A012 1/64. This side is a DCE side, so we need to configure the clocking. Clock rate 64,000. No shutdown. End. IPv6 communications are verified by pinging R2 from R1 and vice versa. Ping 2001 7052 E1CC A012. Oops, we missed the double colon. So :2, and it is successful. On R2, we ping R1 2001 7052 E1CC A012 :1. Notice that the same ping command is used as with IPv4. The only difference is that the destination is an IPv6 address. The ping command sends ICMPv6 echo request messages to the IPv6 destination address. The exclamation mark indicates that the ICMPv6 echo reply messages from the destination interface have been received, therefore verifying end-to-end communications. ICMPv6 is discussed in more detail in Lesson 5, ICMPv6 and Neighbor Discovery. This lesson explained the basics of IPv6 addressing. The preferred format of an IPv6 128-bit address was discussed, as well as ways how the notation of the address can be reduced. There was an introduction to the different IPv6 address types: unicast, anycast, and multicast. The IPv6 prefix length and the basic structure of a global unicast address were discussed. The simplicity of subnetting an IPv6 address using the subnet ID or extending the subnet ID on a nibble boundary was also acknowledged. Subnetting within a nibble can be done, but it is a little more difficult and not recommended. IPv6 address configuration using CLI was demonstrated in a short lab exercise. Welcome to Module 2, IPv6 Operations. In the second lesson of this module, you will learn more about IPv6 address types.
This lesson
examines the different types of IPv6 addresses in detail. Global unicast configuration methods, both manual and dynamic, are described. It explains and provides examples of enabling IPv6 on router interfaces using various methods. Link local addresses are described using static and dynamic iOS configuration examples. Loopback, unspecified, and unique local unicast addresses are also discussed. Assigned and solicited node multicast addresses, along with anycast addresses, are described as well. In the lab exercise, we will learn how to configure and verify various address types. This lesson further examines the three types of IPv6 addresses that were briefly introduced in the previous lesson: unicast, multicast, and anycast. These are illustrated here in more detail. This lesson begins with unicast addresses. The most significant are global unicast addresses, which were also introduced in the previous lesson. The next type of address covered is link local. These unicast addresses are confined to a single link. IPv6 routing protocols use link local addresses to exchange updates and other routing messages. The remaining unicast addresses do not have many options and will require little explanation. The following table shows the IANA's allocation of IPv6 address space. Each of these allocations is discussed independently later in this lesson. The remaining portion of IPv6 address space is reserved for IETF for future use. The following figure shows the generic structure of a global unicast address. The previous lesson examined a /48 format that is typical for most sites, but this figure illustrates a more general structure without the specific size of the global routing prefix. This shows how address space can be allocated to the regional Internet registries and Internet service providers. These are minimum allocations, which means that an RIR will get a /23 or shorter, and ISP will get a /32 or shorter, and a site will get a /48 or shorter. A shorter prefix length allows for more available address space. Possible home site prefix is /56, and subnet prefix is /64. A device, or more accurately an interface, can be assigned a global unicast address manually or dynamically. The following figure shows the various configuration options. Manually configuring a global unicast address has several options. These are the ways to manually configure a global unicast address. Static. Static configuration is similar to configuring a static IPv4 address. The IPv6 address and the prefix length are both configured on the interface. EUI64. This type of configuration allows you to specify the prefix and the prefix length, while the interface ID is created automatically. IP unnumbered is the same in IPv6 as in IPv4. It allows an interface to use the IP address of another interface from the same device. With the Extended Unique Identifier, or modified EUI64 process, the prefix network portion of the address is configured manually, while the EUI64 process is used to automatically assign the interface ID. The modified EUI64 process uses the interface's Ethernet MAC address to generate a 64-bit interface ID host portion of the address and therefore requires a /64 prefix. Global unicast addresses can also be configured dynamically without any manual configuration. Two ways to dynamically configure global unicast addresses are as follows. Stateless Address Auto-Configuration, SLAAC. Using this method, the interface ID is created using EUI64, while the prefix and prefix length are determined from ND router advertisement messages. DHCP-v6, Dynamic Host Configuration Protocol for IPv6, is similar to that of DHCP for IPv4. A device can automatically receive its addressing information by using the services of a DHCP-v6 server. Stateless Address Auto-Configuration uses the EUI64 format shown earlier. By using its Ethernet MAC address, this process allows a device to create its own interface ID, host portion of its address. Combined with another process, Neighbor Discovery Protocol, a host can determine its entire global unicast address without any manual configuration or the services of a DHCP-v6 server. Neighbor discovery and stateless address auto-configuration are discussed in more detail in Lesson 5. ICMPv6 is a much more robust protocol than the ICMP for IPv4. ICMPv6 contains new functionality and improvements. Neighbor discovery uses ICMPv6 to exchange the messages necessary for its functions, specifically 5 new ICMPv6 messages. Router advertisement (RA) messages. Router solicitation (RS) messages. Neighbor solicitation (NS) messages. Neighbor advertisement (NA) messages. Redirect messages. Only the first 4 messages are relevant to the introductory discussion on stateless address auto-configuration. The following figure shows a simplified version of the stateless address auto-configuration process. Step 1. PC is configured to obtain its IP addressing automatically. Since booting up, the PC has not seen a router advertisement message, so it sends out a router solicitation message to inform the local IPv6 router that it needs a router advertisement message. Step 2. Router receives the router solicitation message and responds with a router advertisement. Included in the router advertisement message are the prefix and prefix length of the link, along with its own address as the default gateway. The default gateway address that the router propagates is actually its link local address, not its global unicast address. Step 3. PC receives the router advertisement, which includes the prefix and prefix length for the local network. Using modified EUI64, the PC assigns its interface ID and prepends the prefix from the router advertisement to create its global unicast address. The address is in the tentative state until its uniqueness is verified in the next step. Step 4. Because stateless address auto-configuration is a stateless process, there isn't any device keeping track of all the global unicast addresses on the link to prevent duplication. So, it is up to the host itself to make sure that it didn't create an address that is already used by another device. This neighbor discovery process is known as duplicate address detection. It is nothing more than a device sending its address out to everyone on the link to see whether anyone else is using it. PC sends a neighbor solicitation message with its own global unicast address as the target address. If another device has this address, it will respond with a neighbor advertisement message. If PC does not hear a response to its neighbor solicitation message in the form of a neighbor advertisement, it can rest assured that its global unicast address is unique. DHCP can be a stateless or a stateful service. A stateful service remembers client state from one request to the next. A stateful DHCP server must maintain an accurate listing of available addresses so that it does not give out duplicates. A stateless service does not keep any state information. As the name indicates, stateless address auto-configuration is stateless. After the host creates its own unique address, without the services of a stateful DHCP-v6 server, it will need to verify that its address is indeed unique. Whether a host that is configured to obtain its addressing information automatically uses stateless address auto-configuration, or DHCP-v6, depends upon the configuration of the router's router advertisement message. The RA message can be configured to instruct devices in the link to use stateful DHCP-v6 auto-configuration rather than stateless auto-configuration. The ability for a device to dynamically determine its own global unicast address without the need of a DHCP-v6 server is a significant advantage in IPv6. In an Internet of Things, IPv6 devices, such as webcams and sensors, can just be powered on and can obtain all their addressing information from the router and the EUI64 process. Devices configured to obtain their IPv6 addressing information automatically can use one of the following methods: stateless addressing using router advertisements, or stateful addressing using DHCP-v6. The following figure illustrates this progression in steps to determine whether stateless or stateful auto-configuration will be used. Step 1. PC sends out a router solicitation message unless a router advertisement message has already been received. Step 2. Router advertisements have a 1-bit field known as the Managed Address Configuration Flag, or M flag. When this flag is set to 0, it informs the devices to use stateless address auto-configuration. If the flag is set to 1, it indicates that the device needs to use stateful auto-configuration, DHCP-v6. Now that PC recognizes that it must use stateful auto-configuration, it begins the process to obtain its addressing information from a DHCP-v6 server. Step 3. PC sends out a DHCP-v6 solicit message to a special multicast address specifically for DHCP-v6 servers, FF02:1:2. Step 4. One or more DHCP-v6 servers respond with a DHCP-v6 advertise message, indicating that they are available for DHCP-v6 service. If PC receives multiple advertise messages, there is a process that generates a server preference value that it will use to select the appropriate DHCP-v6 server. Step 5. PC will respond to the selected server by sending a request message, asking for configuration parameters, including IP addresses. Step 6. The DHCP-v6 server responds with a reply message containing the assigned addresses and other configuration parameters. Even though PC obtained its address from DHCP-v6, a stateful service, it will still use the Duplicate Address Detection (DAD) process to ensure that there aren't any other devices on the link with this address. Step 7. PC sends out a neighbor solicitation (NS) message with its newly obtained global unicast address to all devices on the link. The source address is an unspecified address, because PC's global unicast address is tentative until proven to be unique. The destination address is a solicited node multicast address, which is similar to that of a broadcast address. If any devices on the link have the same address, that device will respond with a neighbor advertisement message. Link local addresses are unicast addresses that are confined to a single link. Routers will not forward any packets with link local source or destination addresses. Link local addresses provide a unique benefit in IPv6. A device can create its own link local address completely on its own, without the service of a DHCP-v6 server or a router advertisement message. The following figure shows the format of a link local unicast address. Link local unicast addresses are in the range of FE80:10. Using this prefix and prefix length gives the range of addresses from FE80:10 to FEBF:10. Link local addresses are used in the following ways. Routers use their link local address as the default gateway address in their router advertisements. Routers running protocols such as EIGRPv6 and OSPF-v3 employ their link local addresses to establish adjacencies. Dynamic routes in IPv6 routing tables use link local addresses as their next hop addresses. Link local addresses are configured in one of three ways. Dynamically using EUI64. By default, devices automatically create their own link local unicast address without the assistance of another device, such as a DHCP server or a router. The 64-bit interface ID is automatically assigned either randomly or using the EUI64 format. Random Generated Interface ID. EUI64 is a convenient technique for automatically creating a 64-bit interface ID, but it introduces a concern for some users: the ability to trace an IPv6 address to the actual device using the MAC address used to create the interface ID. To alleviate this privacy concern, devices can use randomly generated 64-bit interface IDs. Whether a device uses EUI64 or randomly generated interface IDs is dependent upon the operating system. Cisco routers use EUI64. The trend seems to be for host operating systems to generate their interface ID randomly by default. Statically, entering the link local address manually. Dynamically assigned link local addresses are ideal for most devices, such as hosts. The disadvantage is the lengthy interface ID, which can be difficult to recognize or remember when troubleshooting or verifying network operations. It is easier to use manually configured link local addresses that are more recognizable. Whether the link local address is created automatically or manually configured, before a device uses its link local address, it will perform DAD to make sure that it is unique on the link. An IPv6 loopback address is an all zeros address except for the last bit, which is set to a 1. The loopback address can be used by a node to send an IPv6 packet to itself, typically when testing the TCP/IP stack. It is equivalent to the IPv4 loopback address 127.0.0.1. An unspecified unicast address is an all zeros address, /128. It can't be assigned to an interface. It is used as a source address to indicate the absence of an address. The source IPv6 address of PC's neighbor solicitation message is an unspecified address because it does not yet have a valid IPv6 address to use. These addresses are expected to be globally unique, but should not be routable in the global internet. They are to be used in a more limited area, such as within a site or routed between a limited number of sites. The following figure illustrates the format of a unique local unicast address. Unique local addresses have the prefix FC00 /7, which results in the range of addresses from FC00 /7 to FDFF /7. IPv4 embedded addresses are used to represent an IPv4 address inside an IPv6 address. These addresses carry an IPv4 address in the last 32 bits of IPv6 addresses and are used to help the transition from IPv4 to IPv6. There are two types of IPv4 embedded addresses: IPv4 compatible IPv6 addresses, which are deprecated. The first 96 bits are all set to zeros. The embedded IPv4 address must be globally unique. IPv4 mapped IPv6 addresses. The first 96 bits are all set to zeros, and the 16-bit segment preceding the 32-bit IPv4 address is all ones. Multicast is a one-to-many technique used to send a single packet to multiple destinations simultaneously, in contrast to a unicast address, which is a one-to-one technique that sends a single packet to a single destination. An IPv6 multicast address defines a group of devices known as a multicast group. It is the IPv4 equivalent of 224.0.0.0/4. A packet sent to a multicast group always has a unicast source address. A multicast address can never be the source address. IPv6 multicast addresses have the prefix FF00:8. This is the structure of an IPv6 multicast address. The first 8 bits are 1 bits, FF, followed by a 4-bit flag and a 4-bit scope. The next 112 bits represent the group ID. The flag field indicates the type of multicast address. The two types of multicast addresses are permanent 0, which are well-known multicast addresses, and non-permanent 1, which are transient or dynamically assigned multicast addresses. Scope is a 4-bit field used to define the range of a multicast packet, which allows routers to immediately determine how broadly to propagate it, from interface local to global scope. Assigned multicast addresses are reserved multicast addresses for predefined groups of devices. They have a prefix of FF00:8. The following table shows the format and some examples of assigned or well-known multicast addresses. Notice that, depending upon the scope, a packet sent to the all routers group ID of 0000002 can be confined to a single link, FF02:2, or used for an entire site, FF05:2. In addition to every unicast address assigned to an interface, a device will also have a special multicast address known as a solicited node multicast address. These multicast addresses are automatically created using a special mapping of the device's unicast address with the solicited node multicast prefix FF00:0:0:0:1 FF00:104. Solicited node multicast addresses are used for two essential IPv6 mechanisms, both part of Neighbor Discovery Protocol, NDP. Address resolution. Equivalent to ARP in IPv4, an IPv6 device sends a neighbor solicitation message to a solicited node multicast address to learn the link layer address of a device on the same link. Duplicate address detection allows a device to verify that its unicast address, created using stateless address auto-configuration, is unique on the link. A neighbor solicitation message is sent to the device's own solicited node multicast address to determine whether anyone else has this same address. An IPv6 Anycast address is an address that can be assigned to more than one interface, typically on different devices. In other words, multiple devices can have the same Anycast address. A packet sent to an Anycast address is routed to the nearest interface having that address, according to the router's routing table. There is no special prefix for an IPv6 Anycast address. An IPv6 Anycast address uses the same address range as global unicast addresses. This lesson introduced the three types of IPv6 addresses: unicast, multicast, and anycast. To summarize this lesson, we will once again use the following table, which represents various address types, among which we spent the most time explaining global unicast and link local addresses. The topology we are going to use in this lab exercise was already introduced in the previous lesson. Similar to IPv4, it is typically best practice to manually configure IPv6 addresses on router interfaces. First, we will configure the global unicast addresses on the links between the routers R1, R2, and R3. R1. Configure terminal. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001:7052:E1CC:A012:1/64. Clock rate 64,000. No shutdown. Interface serial 0/1. IPv6 address A013. No shutdown. End. R2. Configure terminal. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001:7052:E1CC:A013:1/64. No shutdown. Interface serial 0/1. IPv6 address A023. No shutdown. End. R3. Configure terminal, IPv6 unicast routing, interface serial 0/0, IPv6 address 2001:7052:E1CC:A013:3/64. Clock rate 64,000. No shutdown. Interface serial 0/1. IPv6 address A023. Clock rate 64,000. No shutdown. End. Let's verify the connectivity between the routers. Ping router 1, which is 2001:7052:E1CC:A013:1. And it is working. Let's ping router 2. It is also working. On R1, ping 2001:7052:E1CC:A012:2. It is also working. Let's verify the running config for router R1. Show running config, pipe section interface. Using the pipe and section keyword, we can list part of the running config relevant to interface configuration. The no IP address output refers to the lack of an IPv4 address. Even if you do not use an abbreviated IPv6 address when configuring the interface, the running config will use the compressed format. You can have both an IPv6 address and an IPv4 address configured on the same interface. This is known as dual stack and will be discussed in Lesson 20. Most of the verification commands that are implemented in IPv4 can be used with IPv6 by substituting IP with IPv6. Let's analyze the output from the show IPv6 interface brief command. R1 show IPv6 interface brief. The output is similar, but there are differences from the show IP interface brief command that is used for IPv4 addresses. Note that the line protocol and the state of both of the serial interfaces are up and up. Although only one IPv6 address was configured per interface, each interface has two IPv6 addresses. The address that begins with FE80 is known as a link local unicast address. It is automatically configured on the interface whenever a global unicast address is assigned. Link local addresses can only communicate with other devices on the same link. Next, we will verify the output from the show IPv6 interface serial 0/0 command. Focus on the global unicast address that was configured along with a link local address. Notice that there are a group of other addresses beginning with FF02, below the header Joined Group Addresses. These are multicast addresses that the router is automatically a member of when the global unicast address was configured on at least one interface. There are also several lines that refer to ND, or neighbor discovery, which is part of ICMPv6. ICMPv6 and neighbor discovery are explained in Lesson 5. In the following example, we configure R1's serial 0/0 interface using the EUI64 format. R1 Configure Terminal Interface serial 0/0 IPv6 add 2001/7052 E1CC A012:/64. EUI64. End. Notice that the command only includes the prefix 2001/7052 E1CC A012, and the prefix length is /64, followed by the EUI64 option. Had the EUI64 option not been included, the interface ID would have consisted of all zeros, which is a valid IPv4 interface address. We will verify the output from the show IPv6 interface serial 0/0 command once again. Unlike IPv4, using the IPv6 address command does not overwrite an existing IPv6 address. IPv6 accepts multiple IPv6 addresses on the same interface. Notice the addition of a second global unicast address on this interface. The interface ID portion was created with the EUI64 format, which normally uses the interface's Ethernet MAC address. But since this is a serial interface, it took the fast Ethernet's 0/0 MAC address for its EUI64 configuration. The Ethernet MAC address can be verified with the show interface fast Ethernet 0/0 command. R1 show interface fast Ethernet 0/0 include burned-in address. Using the pipe and the include keyword, we can list only the line that contains BIA, or burned-in address. Looking once again at the show IPv6 serial 0/0 output, notice that this interface has two global unicast addresses: the statically configured address and the address that was configured using EUI64. Notice that both addresses on this interface are on the same /64 subnet. So, which of these addresses is used as the source address on packets originating from the router when the interface has multiple addresses on the same subnet? This issue is addressed in RFC 3484, Default Address Selection for IPv6, which is beyond the scope of this course. To keep things simple, we will remove the EUI64 created address on R1. The no IPv6 address command with the IPv6 address/prefix length removes the specific address. R1 Configure Terminal Interface serial 0/0 no IPv6 address. End. The show IPv6 interface brief command is used again, this time to verify that there is only one global unicast address on the serial 0/0 interface. The following example demonstrates using the IPv6 unnumbered command. Configure terminal, interface fast Ethernet 0/1, IPv6, unnumbered, serial 0/0, end. R1's fast Ethernet 0/1 interface is configured as unnumbered. IPv6 packets that are sent on fast Ethernet 0/1 will use the IPv6 address of serial 0/0 as their source address. Now that we are familiar with configuring global unicast addresses, let's deal with link local unicast addresses. The following example shows R1's link local address on serial 0/0 using the show IPv6 interface serial 0/0 command. R1 show IPv6 interface serial 0/0. Because a link local address was not manually configured on this interface, one was created automatically using the EUI64 format. Notice in the output that the MAC address of Fast Ethernet 0/0 was used once again, this time to generate the link local interface ID using EUI64. This process was already used in this lab exercise to create the interface ID for a global unicast address on this same interface. Because the same MAC address is used in both of these addresses using EUI64, both addresses will have the same interface ID. Only the prefix, the leading 64 bits, will be different. It is easier to use manually configured link local addresses that are more recognizable. So, we will configure static link local unicast addresses on the links between the routers R1, R2, and R3. We will use the same link local addresses for each interface for each router. This makes it easy to recognize the link local addresses on each router. R1 has the interface ID 1 on all its interfaces. R2 has the interface ID 2 on all its interfaces. And router R3 has the interface ID 3 on all its interfaces. Remember, a link local address only has to be unique for that link because it is not routable off the link. R1. Configure terminal. Interface serial 0/0. IPv6 address FE80:1. Link local. Interface serial 0/1. IPv6 address FE80:1. Link local. End. R2. Interface serial 0/0. IPv6 address FE80:2. Link local. Interface serial 0/1. IPv6 address link local. End. R3. Interface serial 0/0. IPv6 address FE80:3. Link local. Interface serial 0/1. IPv6 address FE80:3. Link local. End. In the following example, the configuration is verified using the show IP interface brief command. Again, notice that for each router, we have configured the same link local address on each interface. A link local address is created automatically whenever IPv6 is enabled on an interface. This can be the result of a global unicast or unique local unicast address configured on an interface, or the use of the IPv6 enable command. If all occurrences of these addresses are removed, the interface's link local address is also deleted. To enable an interface so it can have a link local address without a global unicast or unique local unicast address, the IPv6 enable command is used as shown here. R1. Configure terminal. Interface Fast Ethernet 0/1. IPv6 enable end. After this command is configured on an interface, the router immediately creates a link local address for the interface Fast Ethernet 0/1 using the EUI64 format and MAC address from the same interface. We can verify that using the Show IPv6 Interface Fast Ethernet 0/1 and Show Interface Fast Ethernet 0/1 include burn-in address. Now that we are familiar with both global and link local unicast addresses, let's examine multicast addresses. Assigned multicast addresses are used in context with specific protocols, such as Neighbor Discovery Protocol and EIGRP for IPv6, which are examined in more detail in the following lessons. We can examine which multicast groups router R1 is a member of by using the Show IPv6 Interface Serial 0/0 command. This output indicates that the R1's serial 0/0 interface is a member of 3 multicast groups. R1 will listen for and process any packets with a destination address of these assigned multicast addresses. FF02:1, all nodes multicast group for this link. FF02:2, all routers multicast group for this link. FF02:1, FF00:1, this is the solicited node multicast address for R1's global unicast address on this interface. Welcome to Module 2, IPv6 Operations. In the third lesson of this module, you will learn about ICMPv6 and neighbor discovery. This lesson examines ICMPv6, which is a much more robust protocol than ICMPv4. ICMPv6 error messages are discussed, including destination unreachable, packet too big, time exceeded, and parameter problem. ICMPv6 informational messages, echo request, and echo reply are covered along with multicast listener discovery messages. Neighbor discovery protocol, router solicitation, router advertisement, neighbor solicitation, neighbor advertisement, and redirect messages are examined in detail. The IPv6 neighbor cache and neighbor cache states are also discussed. In the lab exercise, we're going to use Wireshark for a closer look at many of these messages. As shown in the following figure, an IPv6 header with a next header value of 58 precedes every ICMPv6 message. The preceding header does not have to be the main IPv6 header. It could also be one of the IPv6 extension headers that were discussed before. All ICMPv6 messages have the same general format as shown in the following figure. The 3 fields in the message are as follows: type, code, and checksum. Type, 8 bits, indicates the type of ICMPv6 message. Type values from 0 to 127 identify error messages, while informational messages have type values of 128 to 255. Code, 8 bits, provides more granularity for the type field. Its meaning will depend upon the message type. Checksum, 16 bits, used to detect data corruption in the ICMPv6 message and parts of the IPv6 header. Layer 3 devices use ICMPv6 error messages to notify the sender as to why a packet could not be delivered. The following table provides an overview of the different types of ICMPv6 error messages. There are 4 types of error messages: destination unreachable, packet too big, time exceeded, and parameter problem. There are a few others that are beyond the scope of this course. An ICMPv6 destination unreachable message is sent when a packet cannot be delivered to its destination for reasons other than congestion. A significant change to IPv6 is related to packet fragmentation and reassembly. IPv6 removed this task from the router, allowing only the source of the packet to perform fragmentation. When an IPv6 router receives a packet larger than the MTU of the egress interface, the router drops the packet and sends an ICMPv6 packet too big message back to the source. The packet too big message includes the MTU size of the link in bytes so that the source can change the size of the packet for retransmission. The router can fragment an IPv6 packet only if it is the source of the packet. This ICMPv6 error message is also used as part of path MTU discovery, which allows the device to know the smallest MTU in the path to the destination. IPv6 requires that every link in the Internet have a minimum MTU of 1,280 bytes compared to 68 bytes for IPv4. Before a router forwards an IPv6 packet, it decrements the hop limit field by 1. If the hop limit results in a 0, the packet is dropped and an ICMPv6 time exceeded message is sent to the source. This is an insurance mechanism against routing loops used by the traceroute utility to help determine the path of routers to the destination. An ICMPv6 parameter problem error message is generated when a device processing a packet finds a problem with a field in the main IPv6 header or an extension header and has to discard the packet. ICMP informational messages are not employed to report errors, but provide information required for various testing, diagnostics, and support functions. They are used to help devices discover and share information with each other. The following table provides an overview of the different types of ICMPv6 informational messages. There are 3 categories of informational messages: used by the ping command, used for multicast listener discovery, and used by neighbor discovery. There are a few other ICMPv6 informational messages that are beyond the scope of this course. Echo request and echo reply are 2 ICMP messages used by ping, a very common TCP/IP utility. Ping is commonly used to test network layer connectivity between 2 devices. A device sends an echo request to prompt the destination to return an echo reply to verify network layer connectivity. IPv6 uses ICMPv6 multicast listener discovery for the management of multicast groups, basing its functionality on IPv4's IGMPv2, which included a leave mechanism for the host to inform the router that it was withdrawing from that multicast group. Based on IGMPv3, MLD-v2 extends the first version of MLD to support Source-Specific Multicast (SSM) and is backward compatible with MLD-v1. SSM provides the ability for a host to request multicast packets, not only for a destination multicast address, but also from a specific source address as well. There are 3 types of multicast listener discovery messages. Multicast Listener Query. The router periodically transmits host membership query messages to determine which multicast groups still have members on the router's directly attached networks. Multicast Listener Report. This message is sent by the listener to register for a multicast group. The listener can send this message in response to a query or can send it unsolicited, without waiting for a query from the router. Multicast Listener Done. When a listener no longer wants to receive traffic for a particular multicast group, it will send a Multicast Listener Done message to inform the router that it is leaving that multicast group. As described briefly in the previous lesson, neighbor discovery plays an important role in the auto-configuration of IPv6 address. Devices use neighbor discovery for the following reasons. Stateless address auto-configuration, to automatically determine the network prefix, default gateway, and other configuration information. Duplicate address detection, to determine whether a link local or global unicast address it is about to use is already used by another device. Address resolution, to determine the Layer 2 data link address of a device on its network when it recognizes the destination IPv6 address. Neighbor unreachability detection, to keep track of which neighbors are reachable and which are not. Searching for alternate paths. When a router or the path to a router fails, a host actively searches for functioning alternatives. As already mentioned in the previous lesson, when discussing stateless address auto-configuration, there are 5 ICMPv6 messages used by neighbor discovery. Router solicitation message. Router advertisement message. Neighbor solicitation message. Neighbor advertisement message. Redirect message. The following slides examine each message type and the methods used for router and prefix discovery, address resolution, and duplicate address detection. Router solicitation and router advertisement messages are about communications between a host and a router. Routers periodically send router advertisement messages or respond to a router solicitation message from a host on the link. Router advertisement is used to provide hosts with addressing and other configuration information and is an important part of stateless address auto-configuration. Hosts send a router solicitation to prompt routers to immediately send a router advertisement. These messages are used by a device to request Layer 2 address information from another device on the same network, or to provide this information to the requesting device. Neighbor solicitation and neighbor advertisement messages are part of 3 important processes: address resolution, duplicate address detection, and neighbor unreachability detection. Neighbor advertisements are transmitted in response to neighbor solicitations, and are also sent when it's necessary to propagate new information quickly. The host will maintain 2 tables for each interface: neighbor cache and destination cache. They both maintain a list of information to which traffic has been recently sent. The neighbor cache is equivalent to an ARP table in IPv4. Entries consist of IPv6 unicast addresses and their corresponding Layer 2 addresses. Devices maintain this cache from the information received in neighbor advertisement messages. Destination cache includes destinations on other links or networks. In those cases, the entry will be the Layer 2 address of the next hop router. An ICMPv6 redirect message is used to inform a device that there is a better first hop router. It works the same as a redirect message used in IPv4. Using the possible option field in the ICMPv6 header, called Target Link Layer Address, provides the link layer address of the target address, the recommended next hop router. This lesson examined ICMPv6. Two types of ICMPv6 messages were discussed: error messages and informational messages. The ICMPv6 error messages explored were destination unreachable, packet too big, time exceeded, and parameter problem. The ICMPv6 informational messages covered were echo request and echo reply. Multicast listener discovery messages were also examined. Neighbor discovery processes and its messages were discussed in detail. Wireshark was used in a lab exercise to provide a closer look at messages discussed in this lesson. This lab exercise is similar to the one already done in Lesson 2, where we have done a packet analysis of both IPv4 and IPv6 traffic using Wireshark. Now we will take a closer look at the messages learned in this lesson, again using the embedded packet capture feature on the routers and a Wireshark. This is our topology for this lab exercise. In Lesson 2, we had only routers R1 and R2 that were running both IPv4 and IPv6. Now they are running only IPv6, but there is an additional router, R3, that is connected to the Ethernet segment to router 1 and is acting like a host using stateless address auto-configuration. First, we are going to enable IPv6 unicast routing and IPv6 Ceph processing so that we can start the embedded packet capture on all three routers. We have already explained EPC configuration in Lesson 2, so you should be familiar with it. R1. Configure terminal. Unicast routing. IPv6 Ceph. Exit. Monitor, capture, buffer, buffer. Monitor, capture point, IPv6, Ceph, capture underscore point, S1/0, S1/0, both. Monitor, capture point, IPv6, Ceph, capture point F0/1, F0/1, both. Monitor, capture point, associate, capture underscore point, S1/0, buffer. F0/1, buffer. Monitor, capture point, start all. Show history. R2, configure terminal, IPv6, unicast routing, IPv6, Ceph, exit. Monitor, capture, buffer, buffer. Monitor, capture point, IPv6, Ceph, capture point S1/0, S1/0, both. Monitor, capture point, associate, capture point S1/0, buffer. Monitor, capture point, start all. R3. Configure terminal, IPv6 unicast routing, IPv6 Ceph. Exit. Monitor capture, buffer. Monitor capture point IPv6 Ceph, capture point F0/1, F0/1 both. Monitor capture point associate, capture point F0/1 buffer. Monitor capture point start all. If a router is not enabled as an IPv6 router using the IPv6 unicast routing command, it will not send out ND router advertisement messages, but it can still be configured with IPv6 interfaces. Essentially, this turns the router into an IPv6 host. The router can send and receive IPv6 packets, but it cannot route them. In our example, R3 is acting like a host, but we had to enable IPv6 unicast routing and IPv6 Ceph only because embedded packet capture requires it. Now we need to configure the IPv6 addressing per diagram. R1. Configure terminal. Interface serial 1/0. IPv6 address 2001/7052 E1CC A012 1/64. IPv6 address FE80 1 link local. Clock rate 64,000. No shutdown. Exit. Interface fast 0/1. IPv6 address 2001/7052 E1CC :1 1/64. IPv6 address FE80 1 link local. No shutdown. End. R2. Configure terminal. Interface S1/0. IPv6 address 2001/7052 E1CC A012 2/64. IPv6 address FE80 2 link local. No shutdown. End. R3. Configure terminal. Interface fast 0/1. IPv6 address autoconfig default. R3 is configured to use stateless address autoconfiguration. No shutdown. End. For testing purposes, we will use a couple of ping commands to generate traffic between the routers, which we will analyze a bit later, along with various neighbor discovery messages. In the first test scenario, we will ping the global unicast address of router R1 from router R2. Ping 2001/7052 E1CC A012 1. In the second test scenario, another ping command is issued, this time pinging the link local address from router R1 to R2. Ping FE80 2. Remember that a link local address only has to be unique on that link and is never routed off the link. With that in mind, notice that you cannot ping a link local address of R2 without first specifying the exit interface or output interface of the router. As you can see in the failure of the first ping command to a link local address, Cisco iOS requires the use of the full interface name without any spaces. Now we can stop capturing and export captured files to the TFTP server for further analysis. R1 monitor capture point stop all, monitor capture buffer export. TFTP 192.168.6.100/r1.pcap. R2 r2.pcap, R3 r3.pcap. Let's examine the ICMPv6 echo request sent from R2 to R1. Notice all the fields that were discussed previously, beginning with the IPv6 header, including the version and source and destination addresses. Because the destination address in the ping command was a global unicast address, the source address will also be the global unicast address. Now let's examine similar information for the corresponding ICMPv6 echo reply. In both IPv6 packets, the value in the next header field, decimal 58, indicates that an ICMPv6 header follows the IPv6 header. Looking at the ICMPv6 header in both examples gives you a better understanding of these messages. Type. In the echo request, the type is set to 128. And in the echo reply, the type is set to 129. Code. Ignored by the receiver. The code is always 0 for both an echo request and an echo reply. Checksum. The checksum validates the ICMPv6 header. Identifier. This field is used to help match echo requests with their corresponding echo replies. Notice that the echo request and the echo reply have the same value. This value remains constant for the entire sequence of echo requests and echo replies that were generated by this instance of the ping command. In this example, the identifier is set to 0x10CA for this series of ICMPv6 messages. Sequence. This field also helps match echo requests and echo replies, providing a little more granularity. The echo request is generated with a sequence number, and its corresponding echo reply includes that same sequence number. The next echo request increments the sequence number by 1, and the receiver uses that same value in its returning echo reply. In this example, the sequence number is 0 for both the echo request and the echo reply. The next echo request and echo reply from the same ping command will increment the sequence number to 1. Data. The echo request adds 0 or more bytes of arbitrary data. The receiving device echo reply copies this data into the returned echo request. Following two examples show the echo request from R1 to R2 and echo reply from R2 to R1 using the link local addresses. Notice that both devices use their link local addresses as the IPv6 source address of the packet. The remainder of the message is identical to that of the previous ICMPv6 messages. Again, link local addresses are confined to that link. Therefore, R2 is not able to ping the link local address of R3, which is on a different link. In the following example, we will analyze the actual router solicitation message from R3. Looking first at the IPv6 header, notice that the source address is R3's link local address. The destination address is the all routers multicast address FF02 soliciting configuration information from any router on the link. The next header field indicates that an ICMPv6 header immediately follows. Looking at the ICMPv6 header, the type field is set to 133, indicating that this ICMPv6 message is a router solicitation message. Next, focus on the router advertisement message. Router R1 has been enabled as an IPv6 router with the IPv6 unicast routing command. Verify this by using the show IPv6 interface fast Ethernet 0/1 command on R1. R1 is a member of the FF02:2, the All Routers Multicast group, as one of its joined group addresses. This occurs only if R1 was enabled as an IPv6 router with the IPv6 unicast routing command. As an IPv6 router, R1 will send router advertisement messages. Notice that R1 is sending out RA messages using the default of every 200 seconds. The router lifetime determined that this router should be used as the default gateway for 1800 seconds. If the host does not receive a router advertisement from this router in the next 1800 seconds, it should remove this router from its list of default gateways. In the following example, we will analyze R1's router advertisement. Look at the IPv6 header and see that the next header indicates an ICMPv6 header that immediately follows. The source is the link local address of the interface. It is important to note that this is the address that a host will use as its default gateway. The destination address is an all nodes multicast FF02:1. Although this router advertisement can be sent in response to a specific router solicitation message, it is always sent to the all nodes multicast address. The ICMPv6 header provides the addressing and configuration information that R3 and other potential hosts need. The type field is 134, indicating that this is a router advertisement. The current hop limit field recommends that a host use a value of 64 for their IPv6 hop limit field when sending packets through this router. The flags M and O are both set to 0, which means that stateless address auto-configuration is being used, and that there is no additional information available from a DHCP-v6 server. The router lifetime of 1800 tells auto-configured hosts that this router is a valid default gateway for the next 1800 seconds, or 30 minutes, unless updated by another router advertisement. The reachable time is set to 0, and unfortunately, we cannot see any other details because further output has been truncated, which is probably a limitation of embedded packet capture. In the following example, we will analyze router R1's neighbor cache using the show IPv6 neighbors command. Router R1's neighbor cache has an entry for R3. Because the reachable time limit has elapsed, the entry is currently in the stale state. The age column shows the time in minutes that the entry has been in its current state. R3 ping R1. After communication is re-established with R3 using the ping command, the neighbor cache state transitions to reachable. In the following example, the neighbor solicitation message from R3 is examined in more detail. Looking at the IPv6 header, notice that the next header value is 58 decimal. This means that an ICMPv6 header will immediately follow this IPv6 header. The source IPv6 address is the global unicast address of R3. The destination address might be a little harder to recognize. It is the solicited node multicast address of R1. Within the ICMPv6 message, the type field indicates that this is a neighbor solicitation message. At this point, output is truncated again, so unfortunately, we cannot see any other details. In the last example, we will analyze router R1's neighbor advertisement. The IPv6 header shows the next header value of 58 decimal, indicating that an ICMPv6 header will immediately follow this IPv6 header. The source IPv6 address is the global unicast address of R1. The destination address is the global unicast address of R3. Looking next at the ICMPv6 portion, we see that the type field indicates that this is a neighbor advertisement message. The flags show that this message is coming from a router, and this router advertisement is being sent in response to a neighbor solicitation. At this point, output is truncated again, so unfortunately, we cannot see any other details. Welcome to Module 2, IPv6 Operations. In the last lesson of this module, you will learn about enabling IPv6. This lesson will illustrate how to configure the IPv6 addresses using a common topology that we will be using for the following lessons as well. Some of these commands have already been discussed, but some new ones will also be introduced. Global unicast and link local addresses will be configured using different options. This lesson includes examples of the neighbor cache and modification of router advertisement messages for tuning the neighbor discovery parameters. This is the How-To Network live rack physical topology. You can ignore 3 switches, DLS1, DLS2, and ALS2, because we are not going to need them in our topology for this course. And if we remove them, this is what we get. This is our GNS3 common physical topology for this course. Please note the routers R5 and R6, and we will explain their role in the next slide. LiveRack uses 1841 routers, while we are running 3725 routers in GNS3, so bear in mind the difference in serial interface numbering. This is our GNS3 common logical topology for this course. We will use routers R5 and R6 to simulate hosts on the LAN segment behind router R1. Assume that you are the network administrator of company 123 and have obtained the IPv6 prefix 2001/7052 E1CC:/48 from the provider. The network consists of 3 routers, R1, R2, and R3. Each router has a loopback interface attached that is simulating the LAN network behind the router. R1 has 1111 in the 4th hextet. R2 has 2222, and R3 has 3333 in the 4th hextet. Internally, each of the routers is connected with a point-to-point serial link. To help better identify the serial connections, the subnet ID begins with an A0 and ends with two numbers representing the routers connected by the particular point-to-point serial link. The three internal serial networks are, between R1 and R2, A012, between R1 and R3, A013, and between R2 and R3, A023. The LAN segment behind router R1 has subnet ID 0156 because it is connecting routers R1, R5, and R6. Company 123 is connected to its ISP R4 through the 2001-7052 CC1E A034/64 network. As an example of a remote server, the R4 server has the loopback 0 interface configured with 4444 in the fourth hextet. Interface ID of each IPv6 address corresponds with the router number. So based on the subnet ID, you should figure out if the particular IPv6 address belongs to point-to-point, loopback, or LAN interface, while interface ID reveals which router it belongs to. All the addresses shown in topology are global unicast addresses. This is the interface command for configuring a global unicast or unique local unicast address. This is the interface command for manually configuring a link local address. The following command is used to enable an IPv6 interface without specifying a global unicast or unique local unicast address. This is the interface command to configure a global unicast address using the EUI64 format. This is the interface command to delete all IPv6 addresses from an interface, including the global unicast and link local addresses, unless the IPv6 enable command has been configured. Use the following global configuration command to enable the forwarding of IPv6 unicast packets and the sending of neighbor discovery router advertisement messages. The neighbor cache, similar to an IPv4 ARP cache, is displayed by using the following command. A static entry to the neighbor cache is configured by using the following global configuration command. The neighbor cache can be cleared by using the following command. Router advertisement messages can be suppressed with the following interface command. To change the default router advertisement interval of 200 seconds on Cisco routers, the following interface level command is used. To change the amount of time that a host considers this router a valid default gateway, the following command is used. To set the M flag to 1, telling hosts to use stateful DHCPv6 instead of stateless address auto-configuration for addressing information, the following interface level command is used. To set the O flag to 1, telling hosts that additional information is available from a DHCPv6 server, such as DNS-related information, the following interface level command is used. To display IPv6 router advertisement information received from other routers on the Ethernet, token ring, or FDDI link, the following command is used. This lesson was the first in a series that heavily relies on live demonstration. It demonstrated how to configure the addressing for the topology that we will be using in the following lessons. New commands were introduced, as well as some that were learned in previous lessons. Configuring global unicast addresses. This lab exercise begins with configuring the global unicast addresses on each router. Similar to addressing an IPv4 network, it is considered best practice to manually configure IPv6 addresses on routers, servers, and other network devices. This helps in implementing and troubleshooting network operations. The following example shows the configuration of the global unicast addresses for R1 using the IPv6 address interface command. R1. Configure terminal. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001.7052 E1CC A012 1/64. Clock rate 64,000. No shutdown. Interface serial 0/1. IPv6 address A013. No shutdown. Interface loopback 0. IPv6 address 1111. Interface fast Ethernet 0/0. IPv6 address 0156. No shutdown. End. These addresses are verified with the show IPv6 interface brief command. Both the link local address and global unicast address of each interface are displayed. The link local address is created automatically using EUI64 whenever a global unicast address has been assigned. The following examples show the same configurations and verifications for routers R2, R3, and R4 respectively. To speed up the process of configuring these routers, we will copy and paste the config from the template. R2, R3, R4. Configuring link local addresses. Link local addresses were automatically created when you assigned global unicast addresses to the interfaces. Unless configured manually, link local addresses are created using an FE80:/10 prefix and an interface ID using EUI64 process. As previously mentioned, EUI64 involves using the 48-bit Ethernet MAC address, inserting FFFE in the middle, and flipping the 7th bit. For serial interfaces, Cisco uses the MAC address of a fast Ethernet interface. This results in the multiple interfaces having the same link local address. This is acceptable because link local addresses only have to be unique on that link. Using the EUI64 formatted link local addresses makes it difficult to identify the source or destination of these packets, or when verifying a neighbor adjacency with an IPv6 routing protocol. So, it is advantageous to manually configure the routers with link local addresses that make these addresses more identifiable and easier to remember. The following example shows the configuration of link local addresses for R1's interfaces. Configure terminal. Interface serial 0/0. IPv6 address FE80:1 link local. Interface serial 0/1. IPv6 address FE80:1 link local. Interface fast Ethernet 0/0. IPv6 address FE80:1 link local. End. The same address has been configured for each interface. You can verify the addresses by using the show IPv6 interface brief command. The following examples show the link local address configurations and verifications for routers R2, R3, and R4, using an interface ID to easily identify each router. R1, all interfaces, FE80:1. To speed up the process of configuring these routers, we will copy and paste the config from the template. R2, all interfaces, FE80:2. R3, all interfaces, FE80:3. R4, all interfaces, FE80:4. The IPv6 enable command. When a global unicast address is assigned to an interface, a link local address is automatically created. Link local addresses are required on an IPv6 address, while global unicast and unique local addresses are not. There might be times when you want to enable IPv6 on an interface without specifying a global unicast or unique local unicast address. This can be accomplished by using the IPv6 enable interface command, as shown in the following example, which demonstrates the use of this command on R1's fast Ethernet 0/1 interface. The absence of output from the first show IPv6 interface fast Ethernet 0/1 command indicates that IPv6 is not yet enabled on this interface. It has not been assigned any type of IPv6 address. Configure terminal interface fast Ethernet 0/1 IPv6 enable end. The IPv6 enable command automatically creates a link local address. Once again, the show IPv6 interface fast Ethernet 0/1 command is implemented. But this time it verifies the presence of a link local address while indicating the absence of a global unicast address. Using the show IPv6 interface brief command in the following example confirms that the fast Ethernet 0/1 interface only has a link local address and not a global unicast address. Configuring a global unicast address with the EUI64 option. In most cases, it is best practice to manually configure a global unicast address on an IPv6 interface. There might be times when it is advantageous for the interface ID to be assigned using the EUI64 technique. The following example uses the router R1's fast Ethernet 0/1 interface. The show interface fast Ethernet 0/1 pipe include burned in address command in the following example displays its MAC address, which is used for the interface ID of the global unicast address. In the following example, R1's Fast Ethernet 0/1 interface is configured with a global unicast address using the EUI64 format. Configure terminal. Interface Fast Ethernet 0/1. IPv6 address 2001.7052 E1CC 1234 /64 EUI 64 end. The Show IPv6 Interface Fast Ethernet 0/1 command shows the global unicast address as 2001.7052 E1CC 1234 C001 FDDF FE181. This address was created using the following: a prefix of 2001.7052 E1CC 1234. The prefix was assigned using the IPv6 prefix in the IPv6 address command. An interface ID of C001 FDDF FE181 using the EUI process. The MAC address of the interface C201 FD180001. FFFE inserted in the middle, and the 7th bit flipped. This can easily be verified using one of many online MAC converters. The show running config command in the following example indicates that the global unicast address on R1's Fast Ethernet 0/1 interface was configured using EUI64. Notice that the running config does not show the actual address like the manually configured addresses on the other interfaces. Also, note that the only link local addresses displayed in the running config are those that were manually configured. Link local addresses that were automatically assigned to the interface using EUI64 are not shown in the configuration, as is the case with Fast Ethernet 0/1. Removing an IPv6 address. The No IPv6 Address command is used to remove an IPv6 address from an interface. If this command is used without including a specific address, all IPv6 addresses are removed from the interface, including any global unicast addresses and the link local addresses. There is one exception to the IPv6 enable command. If an interface was previously configured with the IPv6 enable command, the No IPv6 Address command will remove all IPv6 addresses except the link local address. You must use the No IPv6 enable command to delete the link local address. In the following example, all IPv6 addresses from R1's Fast Ethernet 0/1 interface are removed. First, verify the configuration of this particular interface. Then, delete the global unicast address using the No IPv6 Address command. Configure terminal, Fast Ethernet 0/1, No IPv6 address. Because the IPv6 enable command was previously used, you must enter No IPv6 enable to remove the link local address. The Show IPv6 Interface Fast Ethernet 0/1 and Show IPv6 Interface Brief commands verify that all IPv6 addresses have been deleted from this interface. enabling IPv6 packet forwarding and ND router advertisements. IPv6 routers are used to forward IPv6 packets. IPv6 routers can also announce prefix, prefix length, default gateway, and other configuration information using ND router advertisements. The global configuration command, IPv6 unicast routing, enables the forwarding of IPv6 unicast packets. If IPv6 unicast routing has been disabled, a router can still be configured with IPv6 addresses on its interfaces. Disabling IPv6 unicast routing causes the following: prohibits the forwarding of IPv6 unicast packets, prohibits the configuration of static IPv6 routing or dynamic IPv6 routing protocols, and disables the sending of ICMPv6 routing advertisements used by Neighbor Discovery Protocol. The output from the debug IPv6 ND command in the following example confirms that ND router advertisement messages are being sent from R1's Fast Ethernet 0/0 interface. In the topology, both R5 and R6 are acting like hosts on R1's LAN and are configured to obtain their IPv6 addresses automatically. R5, configure terminal, interface Fast Ethernet 0/0, IPv6 address, autoconfig, default, no shutdown, end. R6, configure terminal, interface Fast Ethernet 0/0, IPv6 address autoconfig, default, no shutdown, end. Router R1 sends its ND router advertisement messages, including the prefix, prefix length, and default gateway information, out its Fast Ethernet 0/0 interface. Both of the hosts are actually routers running iOS, which uses the EUI64 format for its interface ID. The following example shows the output from their show IPv6 interface brief and show interface Fast Ethernet 0/0 include burned-in address commands. R5, show IPv6 interface brief, show interface Fast Ethernet 0/0 include burned-in address. R6, show IPv6 interface brief, show interface Fast Ethernet 0/0 include burned-in address. Notice that the interface IDs of both their global unicast and link local addresses were generated using their Ethernet MAC addresses and the EUI64 technique. Neighbor cache. The IPv6 neighbor cache or neighbor discovery cache is similar to the ARP cache in IPv4. The neighbor cache is displayed using the show IPv6 neighbors command. In the following example, R1 pings the global unicast address of R5. Similar to ARP in IPv4, R1 sends an RD neighbor solicitation message to obtain the layer 2 MAC address of R5. R5 responds with an ND neighbor advertisement containing its MAC address. R1 uses this R5's MAC address to encapsulate its ICMPv6 echo requests to R5. R5 sends ICMPv6 echo replies in return. R1 ping R5. Show IPv6 neighbors. The output from R1's Show IPv6 Neighbors command displays the neighbor cache on R1 with R5's IPv6 address and corresponding MAC address. The neighbor cache is populated dynamically using neighbor solicitation and neighbor advertisement messages, similar to ARP requests and ARP replies in IPv4, as previously discussed in Lesson 5. Static entries can also be inserted into the neighbor cache. The following example demonstrates how to add a static entry to R1's neighbor cache using the global configuration command. IPv6 neighbor 2001.7052 E1CC 1234 Fast Ethernet 0/0 1234 5678 9 ABC. End. Show IPv6 neighbors. Note that static entries do not age out. Dynamically populated neighbor cache entries can be cleared using the Clear IPv6 Neighbors command. Show IPv6 neighbors. Static entries need to be removed from the config. Configure terminal, no IPv6 neighbor. End. Show IPv6 neighbors. Tuning neighbor discovery parameters. Lesson 5 discussed the neighbor discovery protocol, including neighbor advertisements, in some detail. A router advertisement message is sent periodically or in response to a router solicitation message. It is used to provide hosts with addressing and other configuration information, and is an important part of the stateless address auto-configuration. By default, Cisco routers send router advertisement messages on Ethernet, Fast Ethernet, Gigabit Ethernet, and 10 Gigabit Ethernet interfaces. Many of the router advertisement parameters are displayed in the output of the Show IPv6 interface command, as shown in the following example, with default parameters. R1 Show IPv6 interface Fast Ethernet 0/0. The parameters for router advertisement and other neighbor discovery messages can be configured using the IPv6 ND command. The following example shows some of the neighbor discovery configurations options, specifically when configuring ND router advertisements. Interface Fast Ethernet 0/0, IPv6 ND. Router advertisements. An IPv6 router does not have to participate in the sending of router advertisement messages. RA messages can be suppressed with the interface command IPv6 ND RA suppress. This command will suppress periodic RA messages, but solicited RA messages, router advertisement messages in response to router solicitation messages, will still occur. One of the previous examples illustrated some of the default parameters associated with router advertisement messages. The RA interval is the amount of time in seconds between consecutive router advertisement messages. By default, the router advertisement interval is 200 seconds on Cisco routers. The IPv6 ND/RA interval command is used to modify this parameter, and in the following example, the RA interval is changed to 180 seconds. The RA lifetime defines how long a host should consider this router as a valid default gateway. It does not apply to the other configuration parameters contained in the router advertisement. The RA lifetime has a default of 1800 seconds or 30 minutes on Cisco routers. A lifetime of 0 indicates that this router is not a default gateway and should not be added to the host's default router list. The IPv6 ND RA lifetime command is used to modify the RA lifetime parameter, and in the following example, the RA lifetime is changed to 3600 seconds or 60 minutes. IPv6 ND RA lifetime 3600. The M flag and the O flag in the router advertisement messages are associated with stateless address auto-configuration. The M flag, or Managed Address Configuration flag, tells a host that it is configured to obtain its configuration information automatically, whether to use stateless address auto-configuration or stateful configuration, DHCPv6. The default 0 notifies hosts on the network to use stateless address auto-configuration. When set to 1, this tells the host to use stateful configuration, DHCPv6. To set the M flag to 1, DHCPv6, the IPv6 ND Managed Config flag command is used, as shown in the following example. The no IPv6 ND Managed Config flag command is used to set the flag back to its default of 0. The O flag, or the other configuration flag, informs a host whether additional configuration information can be obtained from a DHCPv6 server, such as DNS-related information. The default of 0 means that there is no additional information available from a DHCPv6 server. When set to 1, this tells the host that additional information is available from a DHCPv6 server. To set the O flag to 1, the IPv6 ND other config flag command is used, as shown in the following example. The output from R1's debug IPv6 ND command in the following example verifies that the M flag and the O flag have both been set. Managed address configuration, other stateful configuration. ND router advertisement parameters that we have changed in the previous examples can be verified using the show IPv6 interface fast Ethernet 0/0 command. In the following example, these ND router advertisement parameters are reset using the no option for each command and verified that it is back to default values using the show IPv6 interface fast Ethernet 0/0 command. Show run interface F0/0. Configure terminal, interface fast Ethernet 0/0, no managed config flag, no other config flag, no RA interval, and no RA lifetime. End. Show IPv6 interface fast Ethernet 0/0. When there are multiple routers on the same Ethernet network, router advertisement messages are sent from all routers unless suppressed with the IPv6 ND-RA suppress command. To display IPv6 router advertisement information received from other routers on the link, the Show IPv6 Routers command is used, as shown in the following example on R5. Final configurations. The following example shows the final partial running configs for routers R1, R2, R3, R4, R5, and R6. R1. Show run, section interface. R2, show run, section interface. R3, show run, section interface. R4, show run, section interface. R5, show run, interface F0/0. R6, show run, interface fast Ethernet 0/0. In the last example, we will verify the configurations by pinging the adjacent interfaces of neighboring routers. R1, ping R2, R3, ping R1, R2, and R4. Although we can ping the interfaces of adjacent routers, we have not yet configured any routing, and therefore, any remote networks are unreachable. Ping R1's interface, facing R2. We will fix this issue in the next lesson, when we start dealing with routing IPv6. But before moving to the next lesson, we will save the configs on all routers in our topology, because we will be using it a lot in the following lessons, and that will save us a great amount of time necessary to configure all the addressing. R1, write. R2, write. R3, right. R4, right. R5, right. And R6, right.